hello everyone. Welcome to the CSP seminar this week. And for this week, we have Dr. Peng Wang to give us a talk on the diffusion models and also with the low-dimensional modeling. So before we get started with the talk, just some brief introduction for Dr. Wang. So Dr. Peng Wang is the currently postdoc research fellow in our department of the CE and working with Professor Laura Bazano and also the Professor Qin Shi. So before this, he got his PhD in the Hong Kong University, the Chinese University of Hong Kong. And his research lies in the intersections of the optimization, machine learning, and data science. And currently, as you can also see from the title in this talk, so he has been focused a lot on discovering the fundamentals for the diffusion models and also large language modeling through the way for the low dimensional modeling. So I think this talk will be a pretty interesting one and also to show some very interesting results as well. So let's welcome for Peng, and also we will have the question and answering at the end of this talk. So you can feel free to raise a question there.
Okay, thanks. Thanks, Louis. Okay. Thanks, everyone. Today I will present my recent work on diffusion models.
Sorry, it's being recorded on Zoom, right? So
I believe, it is. Use my phone. How to use it? This one? This one?
Yes.
Oh, no, actually, but it is like, well, yeah, it'll
Does it work?
No, this one.
Okay.
So if you can use this one. Go ahead. You can adjust you just put on the
That's
and
works.
yeah,
Okay. It doesn't work. Oh, it works, right?
yeah, it
Okay.
works. Yeah, I already.
Okay, good.
I usually put that in my pocket.
Okay, I learned it. Okay, today I will present my recent work on diffusion models, that is understanding distribution learning of diffusion model, well low dimension modeling. Okay. Yeah, before I get started, I will briefly overview the history of generative artificial intelligence. In general, over the past 10 years, generative AI has achieved great success and progress, right? Like some powerful model and the product had been proposed and released. Some typical example like the GAN, transformer, and BERT, clip, right? And some very popular product like the ChatGPT. I think most folks here have used ChatGPT like for question searching and also like the polling paper, right? However, although the generative AI had achieved great success implications, our theoretical understanding onto these models are still very limited because of most of model like the BERT, clip, also like the GPT, right? They're based on deep linear networks. It contains it's very deep and it contains millions of parameters, and it's like a black box. We don't know what happens at the inside the layers. Well, in this talk, I will mainly focus on a special instance of generative model, that is diffusion models. In general, diffusion models consist of forward and backward process. In the forward process, we will gradually add the noise to the data and until it becomes like a pure noise. And in the reverse process, we will gradually remove the noise from the cropped images and then generate a new image. Here, I use animation to visualize the reverse process of generative models, diffusion models. You can see here, start from cropped images. We can gradually remove this noise, right? And then generate some new images. Okay, right? Okay, yeah. In general, diffusion models have found wide application in practice. A typical one like the text-to-image generation, right? We can use DALL-E, this diffusion model, and input a text prompt and then generate some new image. And then some other application like solving inverse problem and also like the control net, input a sketch of the image. You can see like this one, input some sketch of image. Then the control net can generate the details of the image and then generate different style of images.
Yeah. Only diffusion models or also diffusion models with other things?
Yeah. Someone like DALL-E, it should be include some transformer to understand the text prompt. Yeah. Yeah, in this talk, we mainly starting a question of diffusion model on distributed learning. Since it has been shown in the literature that learning or distribution will diffusion models usually suffers from the curse of dimensionality. Specifically, it means some theoretical work have shown that to obtain an epsilon accurate score estimator will diffusion model, the size of training samples grow at the rate of epsilon to minus the nth power. Here, the n denotes the total dimension of images. For example, if we train a diffusion model, right, on several 10 dataset, the total dimension is about 3,000. Then to obtain the epsilon equals to 0.1 estimator of the underlying distribution, how many samples we need is about 10 to 3,000 power number of training samples. It's incredibly large, but this is not the case in practice. Like we train a diffusion model on this CIFAR 10 dataset, right? You can see we plot the generalization score. We will specify this later. The generalization score is to measure the generalizability of diffusion models against the data size. You can see as the number of sample increase, the x-axis, the generalized score increase significantly, right? After the number of samples is larger than like the 2 to 10th power, right? And like the number of samples is larger than 2 to 14th power, the diffusion model can generate new images that never exist in the training data sets. So here is about, we only need like the 10,000 images to, then diffusion model will generate, right? Instead of like the theoretic bound, 10 to 3,000 power number of training samples. Yeah, and some concurrent work also demonstrated this point. So this brings us a big gap between theory and practice, right? So in this work, we mainly studied the following problem, that is, when and why diffusion model can generate new samples without suffering from the curse dimensionality. Note that in this question, we have two sub-questions, right? Two sub-questions. The first one is when and why diffusion model can generate new samples. The second one is when diffusion model generate new samples, why it doesn't suffer from curse of dimensionality. So in the following talk, we will mainly answer these two questions. Okay, any questions? If not, we go ahead. Yeah, here are some main references. The first one is our this year SML publications, and it also get a best paper award in iClear workshop, right? New Rips workshop. Yeah, and the second one, the third one is our recent archive paper, and the third one just got accepted by New Rips. Unfortunately, the second one it got rejected, although its score is better than the last one. I don't know why. Yeah. Okay. Well, before we introduce our main result, I will briefly introduce the problem setup. Yeah, as we said, diffusion model mainly consists of forward and backward process, right? In the forward process, we gradually add the Gaussian noise to these clean images until the image become like a almost pure noise. And this process can be described by the following stochastic differential equation. And in this equation, the f and g, these two functions are predefined diffusion and drift functions. They are used to control the noise schedule, the adding noise schedule. And this WT here is a standard window process. Well, here we use P data to denote the underlying distribution of data, and this PTX to denote the probability density function at xt. For short, we just call PDF. Okay, yeah. Condition on the input, this condition on this image x0, we can write the PDF of xt as follows. Actually, the standard, the normal Gaussian random vector, right, is a Gaussian random vector with mean xt at x0, and the covariance is like this, is identity. Yeah, after some scaling. And this two scaling st and sigma t depends on the predefined diffusion and drift functions. Well, we can also formalize the backward process that follows. That is, we gradually remove the noise, right? And this process can be described the following ODE, ordinary differential equation. Yeah, you can see this in this equation, a key component is this score function, right? usually in practice, it has been shown in the literature, if this score function is known, then the backward process has the same distribution as the forward process. Yeah, however, in practice, this score function is unknown because we don't know the underlying distribution of the image data. Like for some image data, like the ImageNet or Silverton, right? It's very, very complicated, and the underlying distribution is almost impossible to access. So what we have is only some training sample from this underlying distribution denoted by P data. Okay. Then the remaining question is, if we want to generate images, right? We need to learn this score function from this training data. Yeah. So in the literature, a common approach that follows, just use a network to approximate this score function. You can see here in the literature, we will construct the neural network denoted by S theta, right? The input is xt at different time step. This network is parameterized by this parameter theta. Usually this network in practice is highly parameterized, contains like the billions of parameters. Yeah, a typical one architecture for this network is like UNet. Another one is someone they use a transformer to parameterize this neural network to approximate the score function. Then to learn the network parameters, we can consider the following the training loss. Yeah, our goal, right, is to learn a neural network that approximate the score function at different time t. Yeah, then the training loss is as follows. We minimize the L2 norm between the score output of the network and the score function, right, at different time. And also, we need to consider the integration over the data, right? And different time, the xt at different time. Yeah, and here the ct is a positive weight function. In practice, how to optimize function? Actually, it's very simple. We just sample the training data from this underlying distribution and also choose some time t and sample noise from this from the Gaussian, and then run the stochastic gradient descent to optimize this function. Any questions? Yeah, okay, we go ahead. Well, based on the above preliminary setup, we can first present some interesting empirical findings. We found that when we train different models, there is a phase transition from memorization to generalization regions. Yeah, and here, so the first question is how to quantify the memorization and generalization, right? Here we propose the following metric. The name is self-supervised copy detection similarity. We use this notion to denote it. That is MSSCD, this score. Here, let's take a look at this image. You can see this figure. Like we have two images, that is X1 and X2, okay? Then we want to compare the similarity between these two images. What can we do here? We use this neural network. We denote as CD. Actually, this is neural network. This is a map. Is a neural network that map this image from the image space to the future space. Map it to vector in the future space. Then we compare the similarity between these two future vectors. You can see we just compute the cosine similarity between these two future vectors. Okay. Obviously, this similarity should range from -1 to 1, right? Yeah, if it's like close to 1, then they are very close to each other. Otherwise, they should be very different. Okay, then based on this similarity, we can further define the generalization score. For short, we just call GL score. The GL score is to define GL score, we need to access some training samples and also some generated images from the diffusion model. Yeah.
Is there some like significance to using something other than like structural similarity, or like some of the more common methods for determining similarity? Like
you mean the define? Yeah, you mean the other metrics to define this, right? Yeah. Actually, in the literature, there are many different metrics. We just use one of them. Yeah. Yeah, and this GL score is defined as this equation. You can see here 1 minus something, right? Let's go to the details. You can see this one is actually the empirical probability. This is I is the indicator function. Let's take a look at what is this, right? Given an image xj, we want to find the image that is close to this image in the training data sets. This yi is the training samples. You can see we maximize this similarity, right? We want to find the closed image to this image xj in the training data sets. Yeah, so if this similarity, the closed image to this xj is larger than this similarity is larger than 0.6, this indicator function is 1, otherwise 0. So intuitively, this means if this GL score is small, that means we just memorize the training data. Otherwise, and this also further implied, this diffusion model has a weaker generalization capability. And if the GL score is large, then we have a weaker memorization capability, but a stronger generalization ability. Yeah. Any questions for this metric? Yeah, in some sense, this score should be named as memorization score, right? Instead of generalization score. Yeah. Because here we think if diffusion model has strong memorization, then it has weaker generalization, right? This score can only measure the capability of memorization capability of diffusion models instead of generalizability in some sense. Okay. Then we plot this generalization, this GL score against the number of training samples as follows. You can see here in this figure, we train a DDPM on several 10 datasets. The x-axis denote the number of training samples. As the number of training samples increase, right? You can see the generalization score there's a sharp increase here, right? At this time, at this range, at this interval. Yeah. You can see when the number of training samples is larger, about 10,000, the diffusion model enters the generalization regime. And we also test this GL score on other data sets like the syllabus A and also FFHQ, this image, this phase images. We observe the similar phenomenon. There's a sharp phase transition from memorization to generalization, right? Yeah, we should notably here, the memorization regime, we mean the diffusion model just memorize the training data, right? Instead of the generate new samples. But in the generalization regime, diffusion model generate some new images that never exist in the training data sets. You can, based on this, the definition of GL score, right? Okay. So according to our experiments, we draw the following conclusion, that is, as the number of samples increase, diffusion model transition from a memorization to generalization regime, and it doesn't suffer from the curse of dimensionality, right? Because we just need 10,000 number of images to enter generalization regime, but the theoretical result is about 10 to 3,000 power, about 20 images. Oh yeah, good question. Yeah. We tried some like the 0.7 or 0.5 around this. We can still observe this similar sharp phase transition. Yeah, it's not very sensitive. Yeah, it's just because some previous literature they both use this 0.5. We also use this. Yeah. Okay, we go ahead. Yeah, and there is another work found a similar phenomenon to us. That is this year actually a best paper from Stephen Malan's group. Yeah, we also submit our work to this actually, right? But it got rejected. They got a best paper. Yeah, you can see. Let's take a look at what happened in their experiments that focus on the first two rows. You can see the first row they train a diffusion model on a syllable A dataset subset that is denoted as one. This second row denotes the image generated by diffusion models, second row. And the first row is the closed images to this generated images in the training data sets. You can see here, when the number of samples is smaller than 1,000, you can always find an image that is almost same to the generated images, right? In the training data sets. But when the number of training samples is larger than like 10,000 and then 100,000, the generated image is totally from the training images, right? Yeah. This is very intuitive, right? And they also visualize the distribution of cosine similarity between the generated images and the training images. You can see that the yellow pixels, just focus on the yellow pixel. You can see here, when the number of samples, like the 10, this similarity between the generated image and the training image is almost 1, right? Concentrated around 1. Yeah, but as the number of training sample increase, it decreased to 0.75. Yeah. This also demonstrates the transition from memorization to generalization. Yeah. Okay. Any questions? If not, go ahead. Then we want to answer questions that is what diffusion model learn in the memorization regime, and also what diffusion model learn in the generalization regime, right? So we first study the memorization regime. Our argument that is diffusion model learns the empirical distribution over the training samples. That is actually the multi-delta distribution over the training samples yi. Yeah. To validate, to support our argument, we conduct some theoretical and also empirical studies. You can see, first we take a look at this optimization problem. The main insight here is when the number of samples is sufficiently small, and we know usually the diffusion model use like the UNet and transformer is highly parameterized, right? It contains like billion of parameters, much larger than the training samples. Then in this case, the training loss is like this neural network S. It's like a free optimization variable. Yeah, then we can directly optimize this problem at different time t. And this problem admits the following closed form. Yeah, then we usually in the literature they call this one as an empirical optimal score function. It takes this form. Then we'll measure the similarity between this empirical optimal score function and the learned score function. Use this reproducibility score. Yeah, this reproducibility score defined as this actually is to measure the similarity between the learned distribution by diffusion models and this empirical optimal score functions. Yeah, this two. You can see when the number of samples is small, they are very similar, right? This score is large. But when the number of samples increase, they are very different. That means because diffusion model enter the generalization regime, it doesn't learn the learn the empirical distribution, right? And we also realize the training loss of diffusion models. When the number of sample is small, the training loss is almost 0, right? Because it's now the diffusion, because of all parameterized network, it overfits the training samples. That is why it's very close to 0. Okay. The next question is what diffusion model learn in the generalization regime? Our argument is diffusion model actually learns the underlying distribution. Yeah, as I just mentioned, usually in practice, the underlying distribution of real-world data like the ImageNet and the Semantic, right, is could be very complicated. It's not almost impossible to access. So we need to assume some underlying distribution to verify our argument, right? So here we consider a very simple distribution that is a mixture of low-rank Gaussians. In the later, we will motivate why we use this assumption. It just take this form, right? It's a average over a norm distribution with mean 0 and different covariance. And this covariance matrix is low rank because this UK of size D times R, and this R should be much larger than D. Yeah, then we can, since this distribution is given, we can directly compute the true score function, right? And we can also use this distribution to generate some training samples and then train a different model on these samples, right? That is this one, the learner score. Then we compare the difference between these two scores. You can see as the training sample increase, this score gradually decrease. That means as the training sample increase, diffusion models gradually learn the true distribution, right? Because this gap is smaller and smaller as the number of samples increase. Okay. Any questions? Yeah, go ahead.
One question about
Mm.
what do you mean by generalization?
Yeah, good question. You mean what is generalization and what is memorization?
Yeah,
Oh, yeah.
composing like two different interpolating two data points. Like I know like generalization, usually you say that
Yeah, memorization just memorize the training data, right? The diffusion model generates generate a new image that already exists in the training data. You know this, right?
yeah, yeah.
Here we define the generalization as the diffusion model. Diffusion model generate a new image that never exists in the training data.
I think what David's asking in the second part was how are you able to determine that the network isn't just interpolated between two existing points in the data set? Is that what you're...
I see. Great question. Yeah, it's a drawback of our experiment. Yeah, we cannot identify whether the generated image is just interpolation or combination of two images, right? Yeah. It's a great point.
So
Mm.
what's the answer for that?
Yeah, it's still open, I believe, of course, based on our research. Yeah.
Because I think even there was like papers in 1990s that were able to like take 200 images and can combine them in a linear way to produce like a new image.
Yeah. Here, but you can see here, this score doesn't have this problem. Yeah, because we directly compare the difference between the true score and the learned score, right? This one must be generalization because this one corresponds exactly to the true underlying distribution. It doesn't have problem that you said. Our theoretical understanding is based on this assumed distribution. I believe what you said is about the experimental setting, right? Yeah.
Yeah, I think my time was wrong for asking this question.
Yeah, I know. Yeah, your question is totally makes sense, I believe. Yeah. I think that is also the problem when we do the experiments. Yeah. How to define the how to measure the generalization, right?
Can I ask a question
Yes.
about this one? So even if I just compare not a learned score by the diffusion model, but the empirical distribution, meaning point at every data I've seen, to the mixture of Gaussians, then this goes down as the data goes up, right? So how much of this decrease is due to just the fact that we have more point masses versus...
Yeah, but totally makes sense. Yeah. We should also add a line that you said, right? To compare the difference between the empirical distribution against the distance between score of empirical distribution and the true score, right? Yeah. Thank you. Yeah. Okay. Yeah, go ahead.
With generalization, you mean that you generate trace sample that we have never seen in the training data?
Yeah, that is what we use in the experiment.
And does it say anything about that will cover all the domain of the two distribution? We say that our model of diffusion model as a generalization, can we say that it will cover all part of the true distribution and generate data sample from all the...
Yeah, great question. I believe in practice it is difficult because usually the distribution, maybe in practice the distribution have a heavy tail, right? It's tough to learn the tail part in practice. With high probability, the generated samples like a Gaussian distribution, it always generate some samples around the mean instead of the tails. Yeah, so these diffusion models can only learn maybe the distribution around the mean. Yeah, it's not easy to learn the tail information from the training data.
Generalization is not about.
Yeah, I believe just yeah. Yeah, thanks. Yeah, it's also the problem in the nowadays generative artificial intelligence. They have a phenomenon called model collapse, because you always learn the information around the mean, right? If you use this generated data to train another model again and again, then it will come. Finally you will collapse to the mean instead of the lose or other the tail information. Yeah. Okay. Yeah. Based on the above empirical findings, we only understand the when and why diffusion model learn lies in like the memorization or generalization regime, right? We still don't answer why diffusion model can learn the underlying distribution without suffering from the curse of dimensionality. Now we will theoretically understand these questions. Yeah. Before we get further, we need to introduce some new setup. In our previous experiments on diffusion model, we mainly focus on the like the score matching or denoise matching. Here we use another one that is denoise autoencoder based diffusion models. Yeah, this is because when we apply the tweeted formula to the forward equation, we can get this equation that is the post mean equals to xt plus the score function. That means there are some equivalence between the post mean and the score function, right? Up to this xt. So if we can use a denoise autoencoder, this neural network, to parameterize, to learn this post mean, if we learn this well, we can also approximate this score function well, right? So in some literature, they use this one to train diffusion model, like some famous one, EDM diffusion model, right? Yeah, they based on the denoise autoencoder. The training loss is as follows: just minimize the output of denoise autoencoder and the corresponding the training samples. Yeah, the gap, and take integration of the time and also the noise. And in the following, we'll mainly study the optimization property of this training loss based on the low dimension modeling. Yeah, in our previous slide, we use a mixture of low rank Gaussian, right? Why we can use this distribution, this model, because we have some some existing literature, and we also conduct some experiment to validate this distribution is a good approximation of real world distributions, image distributions. Like the first one is some literature like this one, they observe that the intrinsic dimension of image data is usually low, very much lower compared to the ambition dimension. Like you can see the image net, right? It's very high dimensional, but its intrinsic dimension estimated by their paper is just about 40. It's very low. And another one is some recent work argue that image data usually lies on a union of disjoint manifolds. Like image net, right? You have different classes of images, like dogs and turtles, right? They usually empirical findings find that they usually lies on different manifolds, and this manifold usually are disjoint to each other. Okay, and our model, the union of low rank Gaussians is like a linearization of this union of disjoint manifolds, right? Because in practice, this manifold could be nonlinear, but we use a linear manifolds. It's actually a subspace. Yeah, and another observation is based on our experiment. That is, we plot the ratio of the Jacobian, the numerical rank of Jacobian of the denoise autoencoder, based on the trained diffusion models on different image data sets. You can see here, the rank at some time step is very low. Yeah, you can see, right? At the beginning, it's large, but at some intermediate step, it's very low, the Jacobian, the numerical rank of Jacobian. Okay, all of these motivations motivate us to assume the following model, that is a mixture of low-rank Gaussians. We assume X, the training sample from this distribution, is a mixture of this low-rank Gaussians. Actually, there are some existing work. They also consider the mixture model, but they assume this one, that is a mixture of full rank Gaussians. The covariance is identity, right? The full dimension, but the mean is different. It's like this figure. We assume our model is like this. I believe compared to this model, our model make more sense, right? Because you're the image data, you're like the union of low dimension manifold instead of full dimension space, like in full dimension space. Yeah. Okay, then based on the above model, we can compute because this now is known, right? We can further compute the post mean as follows: is take this form is actually the convex combination of data points projected on different subspace. Yeah, and this weight, this WK is softmax weight. Then based on this score, based on this post mean, right, we can further parameterize the denoise autoencoder as follows. Yeah, right? Parameterize into this form, into this based on this form, right? We can further parameterize this as the similar form, but the parameters is this parameters UK is unknown, the subspace is unknown. Yeah, and then our goal is to estimate this network parameters UK from the training data sample from the this underlying distribution. So plug all of the first we consider a very simple case. Just we have one subspace. Okay, that means the training sample is generated by this way, right? It's generated by a low rank space. This is signal and corrupted by some noise. This is inherited noise instead of the noise in different models, added in different models. Then the corresponding parameterization based on our setup, right, should take this form, plugs in this parameterization, the DAE parameterization into the training loss, into this one, this training loss. We can simplify this objective function and show that this training loss is equivalent to this PCA problem. It's very simple and elegant, right? With this network parameterization. And we can further show that when the number of training samples sample from the underlying distribution, we can learn the correct subspace up to the noise, added the noise level. You can see this gap is bounded some constant, right? Time to the noise level. And if the number sample is smaller than this intrinsic dimension D, this D is the intrinsic dimension of subspace, right? You can see this one. Yeah. Then we may learn the correct wrong subspace, right? In this sense, we answer the question. About the cost dimensionality, right? That is, when the number of training samples under this low rank model, when the number of training samples is larger than the intrinsic dimension, different models optimizing the training loss of different models can learn the correct subspace, can recover the correct distributions, right? Up to the based on the optimal parameterization. Okay, and similarly, we can extend our analysis to the mixture of low rank Gaussians. That means we have a k different subspace. We can also do the similar analysis that is parameterize the DAE as this form, as this one, but replace this weight, this soft max weight with the hard max weight. And then we can further show that the training loss of different model is essentially equivalent to the subspace clustering problem. And similarly, we can also show the this phase transition result. That is when the number of training samples in each subspace is larger than the corresponding intrinsic dimension, we can learn the correct subspace. Otherwise, we cannot. We should know that here the phase transition of distribution learning from feeling to success is different from the phase transition from memorization to generalization, right? It's different. Here, when the number of samples is small, we cannot show different models memorize the training data. Yeah, they are different. This is a drawback of our work. Currently, we can still we are still exploring how to use like this model or other model to understand why different model escaped a phase transition from memorization to generalization. Yeah. This result only shows why distribution or why different models learn the distribution from failure to success. Okay, and questions for our result? Yeah, go ahead. You mean in practice? Yeah. So a lot of methods like some work they directly use different models to compute it. You can see here in our work, right? Yeah, you can see we can know the here the lowest point, the duration, then times the total dimension. We view this point. We can compute based on this. We can compute the intrinsic dimension. Yeah.
Yeah. Then my next question is, if you compute the D
Mm.
in your previous, you have a figure with the train phase transition, right?
Yeah, you mean
Use that D, your theorem does that D correspond to the D that occurs in the phase transition of the curve?
Yeah. Great question. Yeah, we have some realization on that. You can see here. Yeah. We conduct experiment at your side, like we have one substrate, right? We can directly solve that PCA problem. It's phase transition like this. The black pixel denotes the failure of recovering the subspace. The white pixel denotes the success. Yeah, you can see TCA we can get a phase transition like that, right? The x-axis is the number of samples, D is the intrinsic dimension. Yeah, and then we solve the use diffusion model to solve that problem. To optimize the training loss, we can get the similar figure, but it has some blurring part at the intersection, right? Yeah, because we use like SGD to optimize that training loss instead like compute a closed form like PCA. Yeah, also like the subspace clustering, you can see the similar behavior. Okay. Well, we have some further interest empirical findings. That is, we found there are some correspondence between the single vectors of the Jacobian of DAE and the semantic mean of images. You can see we can compute like when we train a diffusion model, right? Then we can compute the Jacobian of the pre-trained diffusion model and then extract the single vectors of this Jacobian. We found the first leading single vector of Jacobian corresponds to the gender of the image. You can see we go to positive directions. This figure gradually becomes the women, right? Then you go negative direction, it becomes a man, right? Yeah. And like the third one corresponds to the head of image. And the first one corresponds to the figure. Fat or thin, right? Of this image, and also like the color, right? Different colors from gray to colorful, and like here. And we also conduct like goes to a random direction. We found there's no change. Yeah. So this means the basis, the single vectors of the basis of Jacobian corresponds to different semantics of the images. Then based on this idea, we can achieve a controllable generation of diffusion models, right? Without any training. In our recent work, right? In our recent work, we propose a method named low-rank controllable image editing based on this idea. Yeah, you can see we can control like the mouth shape, hair curvature, and also other different semantics of images. Yeah. Okay, that is almost all of my presentation. Finally, we draw some conclusions. Yeah, in this work, we mainly studied our contribution can be summarized as follows, right? We mainly studied the generalization and memorization regime of diffusion models, and we also understand why diffusion models learn the underlying distribution without suffering from the curse dimensionality. And empirically, we also find a diffusion model. This basis of Jacobian has semantic means. And also we are still doing some new things based on along this direction. The first one is like understand why different model exhibit transition from memorization to generalization. Yeah, this is very tough question. And another one is like, can we use this one to design more efficient method to train different models, and also do better to do more interpretable and controllable data generation for different models. Yeah, and also like the model safety and privacy and robustness, these directions. Yeah, thank you. That's one presentation.
Other questions?
Yeah, go ahead.
Excuse me if I'm not familiar with about justice. I'm gonna try to summarize what you did, and then I'm gonna ask a question. So basically, what I understood overall is diffusion models are good. They don't fall through adverse dimensionality because the data has a low intrinsic dimension, and they are really good at learning and drawing subspaces.
Exactly.
So my question would be, I think that we can, I don't know how much we can do it, but since we can control the dimensionality of the data, the intrinsic dimension, is it fair to say that if you curate the data set where this intrinsic dimension is high, and then you try to learn the model using the models, is it fair to say that the model is gonna fail?
May not. That means if you want to learn, like you said, image data with high intrinsic dimension, right? You need more training samples, right? Yeah, if you have more, you can learn the underlying distribution and generate new images. Otherwise, you can only like the experiment shows just memorize training samples, generate some of my existing ones. Yeah.
Kind of know from, lots of years of computer vision and everything, that if you really want something like very high dimensional, it's noise. So that's not really typically what you're interested in.
Yeah. Usually the data set we use like ImageNet, and also like you can see here some experiment existing results, they show the intrinsic dimension is pretty low. Yeah, this one existing, the popular ones, right? Minis, Silver 10, Silver 8, all this one. Yeah. Yeah, go ahead.
It seemed like in that figure you showed, of like the phase transition between like memorization to generalization.
Yes.
It seemed like that phase transition point actually depended on the model capacity. Like the UNet like scaled up 2 times, like occurred sort of at.
Yeah.
And it seems like it's like scaling almost linearly with this model capacity, assuming that, right? Because it's like a log plot and you're.
Yeah, possibly. Like here, the phase transition point of that is a different size of models, right? The UNet.
Right.
Yeah.
Right. And it
The
seems
phase
like-
transition point is
Exactly, and it seems like if you make the model twice as big, it takes twice as many samples to like reach this phase transition.
Yeah. Like
Rough.
yeah. You can see here if the model is larger, right? The corresponding generalizing score is smaller, right? Maybe because of training, I believe. It's harder to train the larger model, right? Yeah.
Yeah.
Yeah, also the overfitting, right? Yeah. Larger model may easily to overfit the training sample, easy to memorize. Yeah.
That makes sense. I guess what I'm wondering, seeing this, is like, is there a sense in which like these lower capacity models are actually better? Because the generalization occurs sooner because it has less overfitting capacity, right?
Yeah,
But like it seems like the quality of the image it generates must be like not as good.
Yeah. There's a trade-off. Yeah. Yeah, we should. I'm not sure about the question. We need conduct at least more studies on that. like the question you said. Yeah. Maybe it's tricky. Yeah, the trade-off. Yeah. Usually we think about large models performance is better, but seems from this experiment it's not, right? Yeah. Great comments. Yeah, thank you. Yeah.
I think it's somewhat related to croaking.
Yeah, Goroki. Yeah. The
Parameter space, if you're trained for a longer time, it generalizes faster.
Yeah, you mean this model is not well trained, right? We need to train more, right?
No, like for a smaller, like in the parameter space, for the smaller model, you are giving a larger training time.
I see.
In terms of logs. But to larger model.
Yeah, John.
The last what editing.
Yeah, you mean the control, the image control, image editing, this one, right?
How do you come up with, like, if
you were given a prompt like mouth shape, and you come up with the direction, or do you have to sort of handcraft the prompts that you're allowed to use?
You mean can you repeat it?
Like, for example, mouth shape.
Yes.
Is that something that a user can give, or is that something that you give predefined?
Yeah, we use a mask. Just control when we like control the shape of mouse shape, right? Control the mouse shape, right? We keep other part doesn't change, just change this part. We use a mask.
So is that directly from the previous slide where you say there are the sort of top sigma vectors that control directions?
Yeah.
Are those exactly the ones you're using here? The top sigma vectors?
Actually, in this experiment, is not. We also use some other directions information. Yeah, not just that one. Yeah, because usually these semantics are entangled with each other, not totally disentangled. Like your mouse and your face, maybe mouse is close related to your nose, right? Yeah, change one, maybe change another.
How do you
Huh?
Like, how do you, if you say, for
Yeah.
example, hair mounts, how do you come up with the direction that you're gonna do this editing?
Yeah, like I just said, we use mask to fix other semantics.
But the it's changing
Just empirical yeah study. We try different direction to see which one may change the direction, change the semantics, and then use that one.
So it's kind of handcrafted.
Yeah, it's kind of yeah, not just one direction, maybe 3 or 4 many directions could control the shape of image. We use the best one or some combination of these ones to control the mouse shape. Yeah.
So I guess I have a question about this
Yeah.
as well then. So are you saying that like based on this sort of like kind of handcrafted searching that you've done, you found that there's like a common direction that
Yeah, maybe a low dimensional subspace control this shape instead just one direction. Yeah, to control the mouse shape. Like I said, also other literature they show the semantics of images are disentangled instead of are entangled instead of disentangled. Yeah. Okay. Any other questions? Yeah, go ahead.
I don't
Yeah,
know.
go ahead. Yeah, I was
Yeah,
just
fine.
looking to see
Yes,
what-
5 minutes more, right? There's a class here. Okay.
So my question was more like out of the blue, I guess.
Yeah, sure.
So the reason diffusion literature sort of blew up is because of the diversity and the like visual fidelity, right?
Yes.
Like, compared to other models.
Yes.
Like this was so much better. And we've seen that like in like absolute terms, like it's able to do this behavior to some degree of like learning like the lower dimensional inherent dimensions, right? But like did you do any analysis on like using the same